Hello and welcome to this lecture. I'm going to talk about encoding LDPC codes in the 5G standard. We'll begin by looking at a couple of simple ways of encoding using the parity check matrix, and then show a small toy example, and then I'll quickly generalize to the encoding of LDPC codes. Okay. So we saw encoding of Hamming codes before in the previous week, in the first week of this course. The encoding that we will use here will be slightly different. We will not be using the generator matrix. We will use the parity check matrix for the encoding. It's largely similar except for some minor changes. Okay, so let me show you how that works first for a very small example, and then we'll move on to the codes which are in the 5G standard. Okay, so here's the small example I'm going to take. Let's say we have a code. Let's say we have a code with parity check matrix, which is very simple: 110, 011, 101, 100, 010, I'm sorry, 001. This is the parity check matrix. You can see very quickly that it's a 6,3 code. Okay, it's also in systematic form. So if you have the message vector M, which is M1, M2, M3, the code word C will be M1, M2, M3, and P1, P2, P3. Okay, so these are the three message bits: M1, M2, M3. These are the three parity bits, and these are computed. We will show how these can be easily computed using H and M. Okay. Now, what does H tell you? H tells you that H times C transpose equals 0, okay, which in other words is this equation, right? So, 110, 100, 011, 010, 101, 001 multiplied on the right with M1, M2, M3, P1, P2, P3 goes to 0, right? 0, 0, 0. Okay. So now if you look at what this means, this actually means three equations. What is the first equation? You multiply the first row with this guy. So the first row gives you M1 plus M2 plus P1 equals 0. The second row gives you M2 plus M3 plus P2 equals 0. And the third row gives you M1 plus M3 plus P3 equals 0. Okay. So now this is all binary XORs or modulo 2 equations. So this is the same as P1 equals M1 plus M2. This is the same as P2 equals M2 plus M3, and P3 equals M1 plus M3. So this is the way to do encoding with the parity check matrix, if you will. It's just a small rephrasing of the encoding with the generator matrix. You look at each row of the parity check matrix, and if it's in systematic form, you know that one parity bit is directly specified by that. Okay. So there's various ways of writing these things down. So for instance, one more way to write it is you can write H as P and then I, right? So this is 3 cross 3 identity, and P is just this matrix, right? So P would be 110, 011, 101. Okay, and then you can look at the multiplication here in a slightly different way. Pi times M transpose P transpose equals 0. Okay, so what is P? P is P1, P2, P3, the vector of parity bits, and then you rewrite this. You simply get that P transpose, P times M transpose plus P transpose is 0, and you can quickly see that the parity bits P transpose is obtained as P times M transpose. So in other words, if you want to write it differently, P1, P2, P3 is P times M1, M2, M3. Okay. So this is just another way of writing it. It's all the same thing written in different ways. Okay. So, this is the way in which one uses the parity check matrix, and in fact encoding of LDPC codes in the 5G standard also uses the same principle. The parity check matrix is specified, the code word is specified, the message bits are given, and then you use the parity check matrix to compute the parity bits from the message bits. Okay, except that the parity check matrix is not directly in systematic form, you have to do some small manipulation, which is the manipulation I will show you in this lecture. Okay. So, hopefully this is clear. So, one important thing to keep in mind is, so like I said, this is a 3.6 code. Usually when people put messages and code and the code parity bits on top of the parity check matrix, you imagine that the first column corresponds to M1, second column corresponds to M2, third column corresponds to M3, the fourth column is P1, P2, P3, etc. Okay, so this kind of visualization of the code word with respect to the parity check matrix is useful. Okay, so you write down the parity check matrix. The columns of the parity check matrix correspond to the bits of the code word. H times C transpose is 0, so that's the multiplication, right? The bits of the code word multiply the columns of the parity check matrix, and you can associate each bit of the code word with each column of the parity check matrix. This is the same thing we did in the Tanner graph as well. Okay, so this is a very natural association. So you imagine putting the messages on the systematic part of the code word and then computing the parities using the parity check matrix. So, you see here the first thing gives you P1 as M1 plus M2, okay. So, P2 is M3 plus M2, okay. P3 is M3 plus M1, okay. So, directly gives you that, okay. So, this is how this is just the basics of encoding. So, now let us see how to use this with the parity check matrix specified in the 5G standard. There is one little thing to take care of. I will point that out alone, and then you will see the rest of it follows very naturally in a normal easy manner. Okay, so let us get started with that. So in the previous lecture I gave you this example of a base matrix, a toy base matrix with an expansion factor 5 to illustrate how the parity check matrices are specified. This is a 3 by 6 base matrix. Each entry is either from -1 to +4, expansion factor is 5, and each entry is replaced by a 5 cross 5 binary matrix. -1 is replaced by the all 0 matrix, and any other number, say 0 or 1 or 2 or 3 or 4, is replaced by the 5 cross 5 identity matrix, column shifted, column rotate shifted that many times to the right. Okay, so 1 would correspond to the matrix, identity matrix, column shifted by 1 position, like for instance this. So this one, for instance, this one for instance goes out as this matrix, and this all the other matrices are like that. I showed that in the previous lecture. Okay, so what we will do in this class is we will start looking at the base matrix for the actual LDPC codes in the standard. So this is another slide I showed in the previous lecture. This is part of a base matrix for the second BG2, which is 42 by 52 matrix. It's quite large, it's difficult to capture on the screen. So I'm showing just 10 rows and 20 columns of that matrix. The expansion factor is 48. Okay, so expansion is 48. So these two things are just indices which tell you how to look it up in the standard, etc. Expansion is 48, so you'll see the entries go from -1, 0 all the way to 47. Okay, and these are the first 10 rows. So if you notice, this is the message part. Okay, this is the message part. There will be 10 message blocks. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, each message block actually will expand to a 48 by 48 binary matrix. So overall, after expansion, the message part will be 480 bits long. Okay, 10 into 440. Okay, so that's the way 48. I'm sorry, 10 into 48 bits. Okay, so usually we'll consider this in some block fashion, as in the first the message itself will be taken as M1, M2 till M10. Each MI will be 48 bits. Okay, so I'll think of it as a vector, just concatenated to put together the message part. Okay, and then you'll have the parities. This is the first parity, second parity, third parity, fourth parity, fifth parity, so on. Okay, so each PI is also 48 bits. Okay, so it's all expanded. in the base matrix, you have to think of each of these things as a block of bits. Okay. So now if you look at it, except for this 4 by 4 part which I have shown in the box here, this except for this 4 by 4 part, I actually have an identity matrix. Okay. So from this part on, it is just an identity. Okay. So it's similar to the small little example we saw at the beginning of this lecture, just identity and p. Okay. But this first part is not clearly identity. You have these minus ones, the minus ones gets replaced by 0, but you have a 0 which is identity, another right below that there is another row of zeros. Okay. So this is a double diagonal structure. Okay. So this structure is called a double diagonal structure. Okay. So this is important from a performance point of view. So you need some sort of a double diagonal structure like this for the code to have good performance, particularly at high rates. You need this structure. It gives you good performance. So, but nevertheless, this makes encoding a little bit more complicated. But it turns out there is a certain structure here which you can exploit, and the encoding is actually quite simple. The double diagonal structure will work out very nicely. I will show you that. So that's the only complexity in encoding of the LDPC codes in the 5G standard. How to deal with the double diagonal structure in this part here. It's also a small part. So once you deal with that and find out P1, P2, P3, P4, the rest of it is straightforward. Okay. So once you find P1, P2, P3, P4, the rest of it is just identity. You can find P5, P6, P7, so on, as much as you need. Okay. So this is the basic idea behind the encoding. So to illustrate this double diagonal, we will take a toy example, a much smaller example as opposed to a direct example from the standard. We will take a smaller example, illustrate how that works, and then come back and tell you how to apply it in this case as well. Okay. So this is how it's going to work. Of course, we will write a MATLAB program to do this encoding soon enough, but this is how it works. Okay. Okay. So here's my example to illustrate the double diagonal structure. So you see this is a 4 by 8 block base matrix, and the expansion is 5. Okay. So I'm using a little slightly different notation, compact notation, to capture this. I'm going to use this IK to indicate the identity matrix column shifted k times. Okay. So instead of using entries like 1, 2, 3, I'm using I1, I2, I3 just to show it's the 5 by 5 identity matrix shifted like that. And the 0 represents 5 by 5 all 0 matrix. Okay. So I will be 5 by 5 identity. Okay. And then I1 will be 5 by 5 shifted right by 1 position. I2 will be 5 by 5 shifted right by 2 positions, so on. Okay. So this is a matrix. You can see this is a 4 by 8 matrix. This is the message part, M1, M2, M3, M4, and this is the parity part, P1, P2, P3, P4. So you'll see the diagonal structure here. There is a diagonal structure here, double diagonal structure, and then the zeros are all here, and then you have this I2 being the same as this I2 here, and this I1 being different. Okay. So this is sort of similar to every base matrix in the 5G standard as well. If you look at the first 4 rows, the first 4 parity blocks, they will always have the structure. Okay. And the structure is pretty interesting, and it's designed so that encoding can be easy. Okay. So that's what I'm going to show you next. Okay. So like I said, message is M1, M2, M3, M4. I'm not using subscript in the notation here. It's just for easy typing. Hopefully there's no confusion. Okay. So M1 is the same as M subscript 1. Okay. So M1, M2, M3, M4 is 5 bits each. Code word is M1, M2, M3, M4, P1, P2, P3, P4. These guys are also 5 bits each. Okay. So now how does the encoding work here? So we have H times the code word transpose equals 0. I'm going to write each block row as one matrix equation. Okay. So this is a matrix equation. Five by 5. Okay. So there is a 5 by 5 matrices here. So each M1, M2, each one M1, M3, M4, P1, P2 are all length 5 vectors. Once again, there is this transpose here, which I'm sort of not showing in the notation. Hopefully it's clear to you. So I put I1 and then put M1 as a column vector, okay, and multiply and add up. Okay. So I get this equation. and then this is the second block row, this is the third block row, and this is the fourth block row. Okay, second, so it's indicated here, the second block row, third block row, fourth block row. Okay, the first block row. So hopefully it's clear to you how the first block row came. If you want, I can go back here and write it down. So if you put M1, M2, M3, M4 on the right side, the row 1 here corresponds to I1 times M1 plus I3 times M3, right? You can see I1 times M1, I3 times M3 plus I1 times M4 plus I2 times P1 equals 0. Oh, sorry, plus I times P2 equals 0. Okay, so you can see that's what the first row corresponds to, and that's what I've written here. Okay, so each is a matrix equation. All right. So now if you notice, these two are the same, these two are the same, these two are the same. So this comes from the double diagonal structure. Okay, so double diagonal structure gives you this the same things here, and then here these two are the same, and then you just have this I1 P1 left. Okay, so what this is suggesting is you have to add the 4 equations, these 4 block equations you have to add. If you add them, you will see there will be all sorts of cancellation here. These two will cancel, whatever is equal will cancel. Once it cancels, you will be just left with whatever is on the left side, right? I1 times M1 plus I3 times M3 plus I1 times M4, and then the second row I2, I3, etc. Then the third row, and then the fourth row, and here you will be just left with I1 times P1. That's the only thing you will be left with. So of course you can bring it to this side and write equal to 0. So I have brought the I1 times P1 alone to that side and kept it as an unknown. Okay, so you can find P1 from above. Okay, from this equation you can ready-made, I mean this is just a direct equation for P1. Of course you have the I1 here that just shifts the P1 a little bit, so you can reorder and find out P1. Okay, hopefully this is clear to you. So the basic trick is the double diagonal structure is structured such that when you add all the 4 equations, everything cancels except for the first parity block P1. Okay, so that is the secret to this double diagonal structure. You stare at it for a while, and it's been done so that when you add up the first 4 rows, first 4 block rows, only P1 remains, and you can find P1. Okay, once you find P1, you are done, right? The reason is, if you have P1, you go to the row 1. Okay, so you use P1 in the first equation, you get P2. P2 is the only unknown there, and then you use P2, and then you get P3 from the second equation, and then you get P4 by using P3 in the third equation. Okay, so remember the messages are given to you M1, M2, M3, M4. You have to compute the parities P1, P2, P3, P4. You add the 4 block rows, you find P1, and then you use P1 in the first row, right? First block row equation, you get P2, and likewise you use P2 in the second block row equation, you get P3. Then you use, I guess, P1 and P3 in the third block row to get P4. Okay, that's the way this whole thing proceeds. Hopefully this is clear to you. Now this same structure exists in the 5G standards LDPC codes as well. Okay, so it's just a simple case of picking up the structure and using the same thing in your encoding. You find P1, P2, P3, P4. Okay, so once you find P1, P2, P3, P4, okay, this is again the same 5G matrix illustration, part of the 5G matrix 42 by 52. So I'm showing you only a part. You have 10 message blocks, each 48 bits. The parity blocks go as P1, P2, P3, P4, P5, P6, etc. And for the first 4 rows, you can recognize the double diagonal structure here, right? So these zeros are all i's, minus 1s are all zeros, and then 1 is I1, I1, and then you have I itself here. Okay, so when you add it all up, you will get P1. Okay, so you can find P1, P2, P3, P4 using this double diagonal encoding idea. And then once you find that, once you know P1, P2, P3, P4, this P5 is direct from this equation. Okay, see, because if you look at this equation, P5 is the only unknown, so you can find P5. Okay, so it's just diagonal, and then P6 you can find from this equation, and so on. Okay, so that's the simple encoding method. Hopefully you agree with me. It's designed so that it can be implemented quite easily. The matrix itself is sparse, so you won't be doing too many XOR computations in the encoding, and you don't have to remember too much as well, except for maybe the base matrix and how it's generated. Okay, so this is the end of this lecture. In the next lecture, we'll write a small MATLAB code for implementing such encoders. Thank you very much.